All right, hi everybody. We're going to be looking at actually a bit of a review. We're going to be taking a step back from the calculus for the moment and just make sure that we're completely, on the same page as far as exponential functions go. In fact, there's going to be the second video after this is going to look at the inverses of exponential functions. That's the logarithm function. And after we've covered these, we'll look at derivatives for these types of functions. So let's begin. Okay, so an exponential function is a function that's of the form f of x equals a to the x. And exponential functions are all going to basically look like this. It looks like that as if a is greater than 1, this is what it would look like. And if a is less than 1, it's going to look like this. So this is what this would look like when you have a positive constant that's less than 1. Okay, so so these are the shapes of an exponential function. Okay, and so if you're looking at the limit of a to the r for rational number, actually okay, so this you'll see this in the text. For any positive base, a to the x is going to be the limit of a to the r as r gets closer to x. So if x was an irrational number, for example, then the a to the x would be it's the limit as you take the limit of rational numbers that get closer and closer to x. I think this is going to be kind of this is just how you interpret an irrational exponent. It's going to be the limit of the rational exponents as those rational exponents get closer and closer to that irrational number. Now this isn't going to matter too much because you could just kind of plug a to anything up into a calculator. Like you could plug in a to the square root of 2 into a calculator, just get a number, and you don't care that it's irrational, you get a number. But anyway, this is mentioned just because it is a fact. Okay, so going over some of the laws of exponents. First and foremost, for the exponential function a to the x, as long as a is a positive base, and if it's not equal to 1, the domain will be all real numbers. So any value of any real number can be plugged in for x, and it's going to be defined, and the range is going to go from 0 to infinity. Of course, if the exponent is just the number 1, a to the first power, 1 to the x power, well, no matter what value you plug in for x, it's going to give you just 1, right? The answer would come out to be 1 for any of them. Okay, so another fact, a to the x is going to be positive for all x. Doesn't matter if the exponent is negative or positive, it's going to be positive. It's going to have a positive value. And so here are some other properties for any two a and b that are positive and any x and y in the real numbers, positive or negative real numbers. We have these facts. Okay, so if you can split up the exponent, a to the power x plus y is a to the x times a to the y. So the way that you simplify that is you add the exponents together. Or if you split up the exponents, you get multiplication. Okay, now and similarly, a to a power that's a difference of exponents, x minus y, can be written as a to the x divided by a to the y. And a to the x, parentheses, raised, that whole thing raised to the power y is just the same as a to the power x times y. So that you multiply the exponents when you raise an exponential function to a higher power or to another power. And lastly, a times b, product of two bases to the x, is a to the x times b to the x. Okay, so these are the properties, laws of exponents that you can use to to play with exponential functions and split them up and to rearrange them. And now just about the limiting behavior of the exponential function. As we saw in the picture earlier, if the base is greater than 1, then as x approaches infinity, the exponential function also goes to infinity. So, and as x goes to negative infinity, the exponential function approaches 0 in value. If the base is between 0 and 1, then the limit towards infinity is 0, and the limit towards negative infinity positive, is infinity. It shoots up in the other direction. But you can see this just from looking at the pictures that I drew earlier. Okay, let's take this as an example. Let's look at the limit as x goes to infinity of 2 to the negative x minus 1. So let's write this as, okay, well, first I'm going to split up this into two limits. This is 2 to the negative x, the limit of 2 to the negative x minus the limit of 1. Now, the limit of 1 is just 1, so that's no problem. And what I'm going to do is I'm going to write this as the limit as x goes to infinity of, instead of writing this as 2 to the negative x, 2 to the negative 1 to the x power, which is just the limit as x goes to infinity of 1/2 to the power x. What did I just say? If the base is between 0 and 1, the limit is 0. So this thing is 0 minus 1, so this is going to be negative 1. With that in mind, we can actually come up with a little sketch of this, and I'm going to do that right here. So as I said, no, this is, the limit is going to be negative 1. So what I'm going to do is I'm going to draw an asymptote at negative 1, and with that in mind, I can get a couple little pieces of this function. Let's say when x is equal to 0, I know I'm going to have 1 minus 1, it's going to cross at 0, and with that, that's all I need. The limit towards as x goes to infinity, it goes to negative 1, so that means it's going to look like this. This is the graph of y equals 2 to the negative x minus 1. Okay, so now I'm going to introduce a number, e, which is an important mathematical constant. It's a constant like pi. It's special enough that we give it its own symbol, e. In fact, e is pretty much reserved. I don't think that I can think of another area of math where e is used to mean something else. Well, actually, in statistics, e is the error, or like the residuals. But okay. Anyway. So e is the limit of this expression 1 plus x to the 1 over x power as x goes to 0. So you can see on the one hand, 1 plus x is going to get closer and closer to 1, but 1 over x is going to be increasing up to infinity. So what happens when you have a base that's getting closer and closer to 1, but its power is getting closer and closer to infinity? As x gets closer to 0, well, you get a constant e. E is approximately 2.71828, but e is what's called a transcendental number, in that it can't be represented kind of succinctly as like with rationals and square roots and stuff. So it's irrational, but it's also it can only be written approximated by writing out the decimals and stopping at a certain point. Decimals go on forever. There's no repetition at all in the decimal expansion of e. And if the function f of x equals e to the x, so when the base of an exponential function is e, it's called the natural exponential function. And that's important. You'll see why as we get into derivatives and stuff, why e to the x is so special. So a couple of properties. Of course, this just follows from the theorem for all bases. Because e is a constant that's greater than 1, e to the x is continuous. The domain is all r. The range is 0 to infinity. E to the x is positive for all 0. That's true for all positive bases. And then the limits, as x goes to infinity, e to the x approaches infinity. As x goes to negative infinity, e to the x goes to 0. And so as with all exponential functions, y equals 0 is going to be a horizontal asymptote, but that's nothing special for e to the x. That would be true for 7 to the x or even 1/5 to the x. But because e is greater than 1, we have this thing going up to infinity as x gets bigger and bigger. Okay, let's look at this funny little limit. The limit as x goes to 0 from the left of e to the 1 over x. The thing to remember is let's let t be 1 over x. So as x goes to 0 from the left, t is going to be going to what? Well, when x is going to 0 from the left, that means x is negative. So we're dividing by a negative number that's closer and closer to 0. T is going to be approaching negative infinity. And so what I'm going to write, this limit is the same as the limit as t goes to negative infinity of e to the t. Well, I just covered that, right? E to the t, as t goes to negative infinity, this limit is going to be 0. Okay, so what happens to this function as x goes to infinity? The limit of e to the 2x over e to the 2x plus 1. Well, think of it like this. Let's multiply this by e to the negative 2x on the top and the bottom. Okay, so this is going to become the limit as x goes to infinity of e to the negative, or sorry, it's going to be e to the 0th power over e to the 0th power plus e to the negative 2x. Now this is actually just the limit as x goes to infinity of 1 over 1 plus e to the negative 2x. Now what is, let's do another change of variables. As x goes to infinity, we're going to let t be negative 2x. Okay, as x is going to infinity, t is going to be approaching negative infinity, right? And so this is going to be the same as the limit as t is approaching negative infinity of 1 over 1 plus e to the t. Well, what's the limit of e to the t as t goes to infinity? That's going to be 1 over 1 plus 0. The limit is 0, just as before. And so the limit of this expression as, or this limit of this function as x goes to infinity will just be 1. In a sense, the numerator and the denominator are the proportional, like the relative difference between them is going to shrink as e to the 2x blasts off to giant numbers. That plus 1, it becomes inconsequential, and effectively where the numerator and denominator are getting closer and closer to each other in relative terms. I guess you could think of it like that. Well, okay, that's a little review of the exponential function. We'll do a little bit of practice in class. Okay, that's all. Short and sweet. Bye.